welcome to the advanced conduction series. So I talked about the most scariest things already, the Bessel function, the separation of variable, the method of superposition, all these things, right? And I have already ended the chapter fin, okay, from the point of view of advanced conduction. Now I have also talked about the basic definitions for fin, that is fin efficiency, fin effectiveness, right? So let us now today firstly meet another form of Bessel function, that how does it look, okay, and also some graphs of Bessel function to which you must be acquainted for to be able to solve problems in your examinations, okay. Okay, so I forgot to wear my specs. Sorry about that. Now, let me start. This is, I guess, lecture number 17. Okay, if I am not wrong, this is lecture number 17. Okay, I hope my pencil is charged. I sincerely, okay, it is 100% charged. I am lucky now. So, today is lecture 17, right? So now I will show you a very interesting thing. So this is you can see mid autumn semester examination of IIT Kharagpur in 2023. Okay, so here you will get the real feel that how the things will be given in the question paper. I told you that you don't have to memorize anything about Bessel function. No, not the form, not the graphs, and not anything. You don't have to memorize anything, okay. You have to have just the concept that how can I compare my governing equation with the Bessel equation. If that is what you can, then you can solve the problem. Now for that you require a bit of practice, okay. So see, at first I will show you. Okay, this is the form, okay. Just let me see. Yes. Okay, this is another form of the Bessel function. I hope it is visible. If it is not, then I will write it separately. Anyways, I will write it separately. So the form is d dx of x to the power alpha dy dx plus gamma square x to the power beta y equal to 0. Okay. So now let us bring our governing equation and let us try to compare this, okay, because you can be given any of the forms, okay, the form that I have talked about earlier and the form that I am showing you now, okay. So either of the form you you might be seeing in the examination hall, and according to that you have to solve the question. So what was our governing equation? So if you remember correctly, the governing equation was we had this term, and we have this into this. Okay. So this has become very untidy. So let me just copy it and write it clearly, the governing equation, so that we are able to compare this with the Bessel equation. Okay. So I will copy this, paste this here, okay. So the Bessel equation will have only okay this into this into this. So what I can do is write a into here, and I can bring this term here. Now this looks perfect, right? If I have not done anything wrong, it is okay. And if you do that, then your W will be cancelled out. right? This is equal to 0. So ultimately your governing equation becomes eta square d2 theta d eta 2 plus eta d theta d eta minus 2h eta L square by 2k capital H is equal to 0, right? Now what I will do is I will just copy this thing from here, or let me copy this thing where have I written this one. I will copy this thing from here, I will paste it here, and I will keep them side by side. Okay, so what I can do is I can make it a bit smaller, right? Cut it, paste it, I can make it a bit smaller, and I can also I can also cut it, paste it here, and I can make it smaller. Now the two equations are side by side for you to compare. Okay, so firstly what you can do is, see, I think you can already see this, that this thing I can write as d d eta of eta d eta. So can I write this as this thing? So I think I cannot write this like it, right? Or another thing you can do is you can break this one, okay, and you can write x to the power alpha d2y d dx2 plus alpha into x to the power alpha minus 1 d dx plus the remaining term x to the power beta y is equal to 0. So in these two equations you can easily see that this eta is equivalent to x here and theta is equivalent to y here, right? So the coefficient from these two, from this term and this term, you can easily see that my alpha has to be 2, right? And from this term and this term, if my alpha is 2, then is it matching? It is not matching, I guess. So here if my alpha is 2, then it is 2 minus 1, that is perfectly fine, but then I am having a extra 2 here, right? So that I have to see, but let us now see this term and this term. I will come on to these terms later. Okay, so let me just see the equation. I hope I have done it correctly. Okay, let us see what happens. Oh, okay, now I got the thing. What the thing is that, see, if I say that my eta is not equal to 0, okay, that if I mean if I put the point eta equal to 0 outside my domain, okay, then what I can do is I can cancel eta from each term, right? Now you might be asking that eta equal to 0 means x equal to 0, and that I am considering in my problem because I am applying my boundary condition. That is true, I agree with you, but here just for the sake of comparing these two, I can neglect that point. That is, at that point I know my variable only. I mean at that point I know the temperature, okay, because at that point I am given that my T is equal to TB, T base, so I can take out that point from the domain, okay. So now if you see this equation, then you will get d d eta eta d eta. Now it is okay, yes, minus 2h L square kh equal to 0. So now you compare this and this equation. I will again copy it, and paste it here. Okay, okay, that is fine. Now if you compare this term and this term, you directly get alpha equal to 1, right? So let me write it, this and this, you are getting alpha equal to 1, okay. Now if you compare this term and this term, then what you are getting? So here no x is there, so then beta has to be 0, right? And did I have any theta here that I have missed? Yes, there was a theta that I have missed. I am very sorry about that. Okay, so in this governing equation I should have a theta everywhere, right? If I am not doing any further mistake. Yes, I should have a theta. So here also I should have a theta, here also I should have a theta, and here also I should have a theta. So here there is no eta, so beta is equal to 0, and here I have this y and this theta, so these terms are matching. That means my gamma square is equal to this whole term, okay. So my alpha is equal to 0, 1, beta is equal to 0, and my gamma square is equal to 2h L square by kh, okay. Then you can get the gamma, right? The moment you get alpha, beta and gamma, okay, note that you have already got alpha, beta and gamma. So you can compute this expression, see this expression, that is beta minus alpha plus 2, okay. So here the thing is that if my beta minus alpha plus 2 is not equal to 0, the general solution is this, where you have okay. So I think the image quality is not being disrupted if I zoom it. So if my beta minus alpha plus 2 is not equal to 0, then the general solution is given by this one, where it is, I will write it again, x to the power nu by mu, z there is a subscript nu, okay, gamma, this is not nu, gamma mu x to the power 1 by mu, okay. So let us write it, x to the power nu by mu, z subscript nu, mod of gamma mu x to the power 1 by mu, okay. So now I will think that, what is this nu and mu? See, it is given nu in terms of alpha, beta, okay, and mu in terms of alpha, beta, and so nu by mu is that, okay. Now this z, two particular solution corresponding to zv, okay, and to be selected according to this gamma and nu. So if gamma is real and nu is fractional, 0 or integer, okay, fractional, it can be fractional, it can be, if gamma is real and nu is fractional, then z will be this or this, okay, particular solutions. So the general solution will be this plus this. If gamma is real and nu is 0 or integer, then your particular solution will be Jn yn. Okay, so this plus this. If gamma is imaginary and nu is fractional, then it is I. Okay, you have to just write this Ji. Okay, this is this is the Bessel function of the first kind, yn is the Bessel function of the second kind that I have talked about already. Okay, similarly, if you get beta minus alpha plus 2 is equal to 0, then the solution is very simple, it is given by this. Now two particular solutions to be determined according to the roots of this equation, r square. So here r is the variable, you know alpha, you know gamma, so you know you can find the root of this equation, right? You can find the root of this equation. So if in this equation, or see here it is what? Here it is b. So here it is b square minus 4ac. If this b square minus 4ac is positive, right, and we know that this is nothing but the determinant, right? So if this is positive, then we are having two real roots of this equation. If this is 0, I'm sorry, if this is 0, then also it will have real roots but equal roots, and if it is negative, then this equation will have imaginary roots. So if it is positive, then the particular solutions are this r1 and r2, where this r1 and r2 are roots of this equation, 0. Okay, so see, everything is given. The moment you can find this equation, what your job is now to compare it with the general form of the equation, and that is this. And the moment you compare the general form of the equation with that of your governing equation, you get this constant alpha, beta and gamma. The moment you get alpha, beta, gamma, you can find this nu and mu. Okay, the moment you find this nu, mu, gamma, everything, you can find the condition that is being applicable for you. Okay, then you can proceed for the actual solution. Okay, that is how you, that is how you will be dealing with the Bessel function thing. Okay, so let us do one step further in this problem. So here alpha equal to 1, beta equal to 0. Now then we can directly see that our alpha, so what was the expression? We have to find beta minus alpha plus 2. Okay, so minus alpha plus beta plus 2. So what is this? Minus 1 plus 0 plus 2, that is equal to 1. See, this is greater than 0. So which condition is being satisfied here? Okay, so this first case is being satisfied here, that is this is not equal to 0. So this first case is being satisfied here. Okay, then we know that our general solution will be this. Now the moment we know that our general solution will be this, we have to now find this nu, mu and z. Z is the function that we have to know, and nu and mu we have to find. So nu you can find because you know alpha, you know beta. Okay, that is alpha equal to 1, beta equal to 0, right? So then this nu directly comes as 0. And what about mu? Mu is equal to 2 by beta is equal to 0, alpha is equal to 1 plus 2, so mu is equal to 2. See, we got all the thing. Now we have to find z. Now see, here this gamma, gamma is what? Gamma is this one. See, gamma square is this. Okay, now this is positive, this is something positive. Okay, I mean this number, sorry, this number is positive, then gamma must be real, right? Plus minus root over of something. So then we know that gamma is real, gamma is not imaginary, right? So if gamma is real, so then I have this condition. Okay, and what is my nu? nu is 0. So I get this plus this. Okay, then my particular solutions are this Jn and Yn. So my Z will be some C1 Jn plus some C2 Yn. Clear? The moment you get Z, then you know the actual solution. So the only thing you now have to calculate is the two constants C1 and C2 that you will get from the boundary conditions. Clear? Okay. So now your homework will be here to solve this one. Okay, this one. You can take a screenshot if you don't have the problem. You can take a screenshot. This one. I will zoom it a bit more if that helps, and I will read it. A parabolic fin has a cross-sectional area given by, I will write it if you cannot see. Okay, x by L whole square. So now we have worked with a triangular fin. Okay, now this is a parabolic fin. Okay, where W is the fin width, B is the half thickness at the base, L is the fin length, X runs from the tip to the fin inwards. Now here you have to be very careful. X runs from the tip of the fin, X runs from the tip of the fin inwards. So what is the tip of a fin? Now if I draw it here, okay, if I draw it here, the fin will have a shape something like this. Okay, now the tip of the fin is this one, this one. So my x is like this, right? Don't draw the coordinate axis like this, then your mathematical calculations will be opposite, and obviously you are asked to take the x like that in the question paper, so you are supposed to follow the instructions, right? So don't change that, be very careful. It will be assumed here that W much see, these assumptions here are told. It will be assumed here that W is much greater than B and L is much greater than B. Okay, so what is B? B is this height, B is this half thickness. Okay, L is the length. Okay, so it is told that this W is also greater than this and this L is also greater than this. So if I say that, then I am saying indirectly that that is my my heat will, I mean my temperature profile will not vary in this direction B. Okay, because this B is very small, that my heat transfer resistance becomes very small, and that is why to maintain a particular rate of heat flux I don't need a very high temperature gradient. Okay, that is the logic here, and I have talked about it earlier. Okay, the fin base temperature is T naught, the ambient temperature is T infinity, and the heat transfer coefficient is H. Now you see here it is not being told that this L is much greater than W also. So if you need this assumption, just state here. If you need this assumption, I mean, see in the, if you have already seen the previous video, to make the governing equation comparable with the Bessel function, I have used an additional assumption in between the problem. If you need that kind of assumptions to make the problem simpler and being comparable, make the problem being comparable with the Bessel function, if you want that, then you clearly state that assumption in the answer script. Okay, and you write that this is not a very unjustified assumption, it can be the case. Okay, so formulate the steady state governing equation and boundary conditions for this type of fin, determine the steady state temperature profile Tx. Okay, so see here it is written, formulate the dimensionless steady state governing equation. Okay, so you have to do it from scratch. If you memorize and write it, even if it is correct, then it is 10 marks, you will get maximum. If I am the professor, I will give you 2 out of 10. Okay, because you are asked to formulate that. Now okay, so here the main challenge is to formulate the governing equation actually, And also I will say that the comparison with the Bessel function, but I have told earlier that as an engineer you are not supposed to do these kind of things. I mean, you can say that I don't know Bessel function. I can simplify the equation according to your need, but I don't know how to solve it. Okay, that is still acceptable. But you have to formulate the equation. You have to see, as an engineer we have to simplify the daily life problems, and that we can do by modeling the daily life practical problems into the mathematical equations. Okay, now one thing, you have to dimensional, I mean you have to make this dimensionless, and that I have already done here. Okay, so I have converted this t into theta and this x into eta. You have to do the same thing. Okay, so that is your homework. Okay, now one more thing about the Bessel function, then we will move to something else. See, here it is given. Now if you are applying the boundary conditions, okay, so now you are seeing that I am getting here this Jn and Yn. So when I will be applying my boundary conditions, I will be get that at x equal to or eta equal to 0, my theta is prescribed. Then if you have to apply this boundary condition, you have to know that what is my Jn equal to 0. I mean, what is my Jn of 0 and what is my Yn of 0, right? You have to know that. Okay, another thing, J nu fractional, okay, that is fine. See, here if it is 0 or integer, this nu, okay, then here this is z nu. Okay, that means this n is also equal to 0 here. Okay, this n is also equal to 0 here. So that means if I write the final solution, I will get as y, or here it will be theta, that is a function of eta, is equal to x to the power nu is 0, right? So nu is 0, x to the power 0, and z nu is what? Z nu is c1. Okay, c1. Now this I have said this n is nothing but equal to nu, and this is 0, because you see that here I have z, I have subscript of z as nu. Okay, and these functions are nu only. I mean these functions, this nu and this nu are same, and this should be also nu. Okay, these are same, the subscripts are same. Okay, I mean you are calculating this z nu, so z nu will be c1 j nu plus c2 y nu, but this nu is equal to 0, so it will be c1 j0 of what, this mod of gamma you can find from that, and mu is equal to 2 x to the power half plus c2 y of 0 this one. Okay, again into 2 into x to the power half. This is your final solution. You are required to find c1 and c2. So the moment you have to put theta at eta equal to 0, you will get c1 j0. Okay, so this will be not x, this will be eta. Okay, this will be 2 into eta to the power half. Okay, you will be c1 j0 of 0 plus c2 y0 of 0. Now from where you will get this j0 and y0? From this graph. Okay, see, this graph is for j0. So j0 at 0 is equal to 1 from this graph, and this graph is for y0, this is y0. So y0 at 0 is equal to something minus 1.7, that you, or it is going towards, sorry, minus infinity, it has not cut. Okay, these graphs are not having very good quality. This y0 tending to 0 is going to infinity. Okay, so this term is going to infinity, this term is going to minus infinity actually, but this cannot happen, this cannot happen. That means, have you understood, that is, I am getting that this term is going to minus infinity, but I know that theta at eta equal to 0 cannot tend to minus infinity. So to save this fact, I have to satisfy C2 is equal to 0. That means my theta is equal to C1 J0 of 0. Clear? Theta of 0 equal to C1 J0 of 0, and my theta of 0 is equal to, I know that my theta of 0, so my C1 is equal to theta at 0 J0 of 0. Clear? Okay. So now, okay, so now you see another thing, that is, if you are given some theta dash at 0, maybe, okay, I'm just taking a hypothetical situation that in any problem you have got this general solution of Bessel function, and you have to find this theta dash of 0. So then what will be that will be C1 J dash of 0 plus J dash of what? J dash of 0, this is 0th order first kind of Bessel function. This subscript is very important, okay. This is y0 dash of 0. Now you see here properties of Bessel function, derivatives of Bessel function, okay. So here I am getting directly my nu is 0, okay. This, see, I am zooming it, here it is written as nu, x to the power nu. So my ddx of, okay, z0 mx is equal to, okay, again I have my nu is equal to 0, so both these things are 0, okay. So if I put nu is equal to 0 here, then it will boil down to m into z, nu minus 1, nu is 0, so this will boil down to what? M into z minus 1, the subscript is minus 1, mx, okay. And here, okay, now subscript cannot be minus 1, okay, so that means I cannot apply this thing here because I am getting subscript minus 1. I have to apply this thing here, okay. But here it is given a special case of equation 3.136, this equation corresponding to nu equal to 0 is, if I have this one, then this, see, ddx of, see this very carefully, ddx of z0, 0th order z, is equal to minus m first order z, z1. So if I put here z equal to j, so then my j 0 dash mx is equal to minus m j1 mx, okay. Now here you know your m, right? Here you know your m, and what is your m? M is your here this gamma, m is here this gamma, okay. So then you can find that, okay. So you see that my j0 mx, if I take that derivative j dash, that will become j1 of, sorry, j0 mx dash equal to minus m j1 mx. Clear? If this z equal to j y k h h1 h2, if this z is equal to I, then this has to be true. Now this I, k, h, these are nothing but different kinds of Bessel function. You don't have to worry about all these things. You will not be given anything other than j and I, okay. But still I will advise you to read about, or you cannot, you can at least search in YouTube that different kinds of Bessel function. I have only introduced you with the first and second kind, that is the j and y, okay. But you can have other kinds of Bessel function also. But have you understood, that is, if I am having, so let us see actually, that is, if I am having here z0, okay, so y0 becomes y1, obviously there is a minus m here, so y0 becomes y1 and j0 becomes j1. Okay, so here this thing will become c1, so there is a minus m factor will be there, so it will be c1, okay, j1 dash of 0 plus c2 y1 dash of 0, okay, and there will be a minus m factor that I can take out. Now you see you have the graphs for j1 and y1 also. So I can see that this is the graph for j1, okay, and the graph for j1 at 0, at x equal to 0, it is 0, and for the graph of y1 it is still going to minus infinity. So again, if I have to satisfy, maybe you are given a finite gradient of theta at 0, so then you see this thing is again going to minus infinity, which is not visible. So that is why, I mean, because it is not visible that my gradient is minus infinity, that means this has to be 0. So this is how you have to deal with the boundary conditions for Bessel functions. Now I will solve one more problem or two problems, uh, I mean regarding that separation of variable, where I have already talked about the general solutions, okay, where I got, if you can remember that in the method of separation of variable, generally I was having the solution that y equal to c1 sin lambda x plus c2 cos lambda x, but I can have the solution maybe y is equal to c1 j0 of x plus c2 y0 of x. So then to solve that problem of method of separation of variable, you need this concept that how can I put the boundary conditions of Bessel function. So I will give you one homework problem and you don't have to worry about that. I mean, I will solve that in the next video, okay. So that was all about the Bessel function. I have completed the fin thing. So now let us move to another problem, okay. So this is just a problem, people name it as quasi-static heat conduction problem, okay. So the problem is, I mean, I will not say that this is any other kind of problem, you need any other theory, you don't need any other concept or any other theory to solve the problem about which I will be talking about right now, okay. You don't need any new theory, you will need everything that you already know about conduction, okay. So let me start with the problem statement, okay. So I am having a hot furnace, okay, I am having a hot furnace and I am having a long sheet of metal rod. uh, this is not, I mean, technically correct, that is long sheet of metal rod. So maybe it is a metal sheet, okay, long metal sheet. And okay, so if I draw again the 3D view, that will be helpful, I guess. So I can draw it, the furnace, I can draw a 3D furnace, I guess, okay. হ্যাঁ আসলে এসো, অসুবিধা নেই, okay. Sorry about that, actually I am recording the video in my home, so my father was calling me. So this is the furnace and now I have to draw the sheet, okay. So how can I draw the sheet, okay, let me try to bring my drawing skills. I am not a very good painter actually, okay. So forgive me if my drawing is not up to the mark here. What I feel is that to make these kind of drawings, you have to have a good kind of imagination of the 3D view and all these things. Okay, so I think it is you can think about this. Okay, so one more thing that I can do is let me get this precision eraser, and I will join this. Okay, now I think it is clear. So one more thing, I will join this also. Okay, so this metal sheet, this is a metal sheet. So how can I call this as sheet? Okay, अरे यार, okay, you know that this thickness has to be small than the width than the length. So this is T. Okay, now this is W, and this length is very, I mean very large. This is actually a, I can say, a continuous sheet. Okay, this is a continuous sheet. Okay, I mean if you have visited uh, any factory, so they will not pass, I mean a small part of sheets, they will pass a continuous flow of sheets. Okay, so that is it. So this is moving with a velocity. Okay, this moving with a velocity maybe u, clear, and this furnace is having a temperature Tf, maybe T furnace. Okay, and the heat transfer, you can actually it will be by convection and conduction both, and in many cases you will be having vacuum inside the furnace. In that case you will be only having the radiation and not the convection. Okay, so this is Tf, the temperature of the air inside the furnace. So we will be only considering the convection here, and to justify that you can say that the temperature difference between the furnace temperature and the sheet temperature is not very high. If that is not very high, then you can neglect the radiation. Okay, so this is Tf, and now here I will set up a coordinate axis for you. Okay, that is, if I set this up, we will take this green color only. Okay, so this is x. Okay, this is y, and this is z. This is y and z, and this is my origin. Okay, so this point is x equal to 0, this point is x equal to L, where this L is nothing but the length of the furnace. Okay, length of the furnace is L. L. Okay, and maybe you are given the boundary conditions also, that is the ambient temperature is T ambient. Okay, the ambient temperature is T ambient. That means at x equal to 0, the plate temperature will also be equal to T ambient. Okay, but this temperature you are not knowing. Okay, in practical this temperature is not will, when I mean will not be equal to the ambient temperature. If it is given in the problem that at x equal to L, this is equal to ambient temperature or this is equal to furnace temperature, ideally they should be equal to the furnace temperature, right? Ideally this should be equal to the furnace temperature, ideally. Okay, it is not a, I mean necessary fact. This, and practically it will not be equal to Tf, it will be a bit I mean lesser than Tf. Okay, okay, so first of all I will give you a task. I will ask you to solve it by yourself. Okay, that is, can you draw the temperature profile of this rod? Okay, not by solving the problem. I am not asking you to draw the exact, I mean to draw the exact curve, what will be the exact equation. No, I don't want that. I am just wanting the uh, qualitative nature. Okay, so if I draw this here, okay, and not only inside the furnace, but you have to draw a bit, you have to draw up till a distance that is far from outside the furnace. So this length, so this is here in this direction, it is x, this here T. This T is the temperature of the rod. Okay. Now this is, okay, this is L, this is maybe something uh, A. Okay. So if this L is maybe 1 meter, this A is maybe half meters. Okay, not half meters, maybe 1/4 meters. Now you have to draw the qualitative temperature profile. Again I am saying you that, what has happened? Okay, again I am saying you, okay, now I think you can see the total picture. Again I am saying you that you don't have to draw the exact curve, you don't have to think that if it will be parabola or ellipse or anything, but it should show the qualitative nature. Now I am also helping you that what do I mean by qualitative nature. It means that, see, if I am seeing that at my x equal to 0, okay, I am starting from what, t equal to ta, that is okay, that is given, but from that uh, will there be a slope, I mean will there be a curve with decreasing slope or increasing slope? What will be that? That you have to tell. And again from here at x equal to L, so when the curve will be tending towards x equal to L, will there be an increasing slope or decreasing slope, or that may be a constant? And after the curve has just passed the x equal to L, what will be the slope? I mean these things, I mean actually the slope is the main thing that governs the nature of the curve. Okay, so you have to just tell about the slope. So I will ask you to pause the video, think for some time and solve this. So I hope you have tried this. Now what happens is, in the interviews like BARC, like maybe ISRO, DRDO, they will ask these types of questions. Now there, if you answer them, "Ki sir, then I have to solve the governing equation and then only I can draw the curve." No, they will ask you that thing intuitively and then draw the curve. They will just, I mean they just want to know that what is the nature of the curve, what are the slopes. Slopes are very important, okay, because if you don't know the slope, uh, then you cannot actually, I mean cannot make a intelligent guess that what can be the temperature in between. Okay, so now let me draw it. See, here it is T ambient outside, right? Here it is T ambient outside. So with which color I should draw it? With a very bright color, right? So let me see. Maybe this one. This is the brightest color, I think. So here it is T ambient, maybe this one. Okay. Now here it is T ambient and inside the furnace it is uh, TF. So there is a high temperature difference, right? So that means the temperature will rise sharply, okay, but when it will rise something like this, it is not linear. Okay, now here if here it is TF, this temperature is TF, if I am saying this, so the moment you are now maybe at this position at 0.8 L maybe. Now the temperature of the rod has sufficiently increased, right? So at this position of the rod I have T ambient, but the portion of the rod that is at this position, it has passed through all this distance. So it is being, so this part has been heated, this part has been heated sufficiently. So what I am telling is that consider that this part at time t equal to 0, it was at x equal to 0 having ambient temperature. Then at time t equal to tau, it has travelled u into tau. Okay, so this length is nothing but u into tau, and after it has travelled u into tau, it has been heated up to a sufficient temperature. So maybe that temperature is something T dash. So Tf was much greater than Ta, but T dash is not much greater than Ta. Okay, I'm sorry, but Tf is not much greater than T dash. It will be greater than T dash, but not very much greater than. For example, if Ta is 25 degrees Celsius, maybe T dash and maybe Tf is 100 degrees Celsius, okay, then maybe T dash is your 70 degrees Celsius. So the difference has decreased, okay, significantly. That means now the heat transfer rate at this position, that is x equal to u tau, that will be not very much high, because heat transfer rate is governed by the temperature difference, and as the temperature difference is decreasing, I mean with the length, with the increasing length, I hope you are following each and every word. Okay, it is my temperature difference is decreasing with increasing x. That means my heat transfer will also decrease with increasing x. And what is causing the increment of temperature? That is the heat transfer. So if my heat transfer is decreasing with increasing x, that means my increment in temperature with x, that will also decrease. Mark my words very carefully. My temperature difference, what temperature difference between furnace and the sheet, that is decreasing significantly as I am proceeding through the furnace. So if that is decreasing, my heat transfer rate will also decrease. As my heat transfer rate is decreasing, my increment in temperature with x, that will also decrease. And what is this term? What is this expression? That is my increment in temperature with x. That is my gradient of temperature with respect to x. That means that should decrease as I am proceeding through x. Clear? That is the intuitive thing. That means it can be a curve like this, but that will be wrong because here the slope is increasing, you see. So that means it is wrong. Okay, so anyone can say that the temperature will increase, but it will increase with a decreasing slope, and it will not touch Tf. Practically it will not touch Tf, it will be asymptotic with Tf. Okay, now I have drawn it. Now what is happening after this x equal to L, that is after the rod, after this section. Okay, now I am talking about this section only. Now this section has passed, okay, the whole furnace, okay, maybe at x equal to some tau dash, okay, tau dash into u, okay, tau dash is the time at which this portion has passed through the whole furnace. Now after it will come out of the furnace, now again there is a very sharp temperature difference between the temperature of the sheet and of the rod, right? So because it is having a sharp temperature difference, it will have a very high heat transfer rate. And now the heat transfer will be in which direction? From rod to environment or from the environment to rod? Yes, you are correct. It will be from rod to environment because the rod is very hot and the environment is very cool compared to the rod. Okay, so now maybe here the temperature is 90 degree at exit, maybe the temperature is 90 degree and the ambient is 25 degree. Okay, so now maybe after some time x equal to tau double dash into u, I mean after some time x tau double dash, okay, it has covered x equal to tau double dash into u, and this section has come to this one, this section. Now the temperature has been decreased significantly. So now the temperature maybe has gone down to 40 degrees Celsius. Okay. So again the same thing is happening. That is, the temperature difference between the rod and the environment is decreasing with the increasing x. That means my heat transfer rate will also decrease with increasing x. That means my decrement in temperature will decrease. My decrement in temperature will decrease with increasing x. So it will again have a decreasing slope, and if this is my T ambient here, it will asymptotically reach T ambient at a particular. So this will be the nature of the graph. So many of you have maybe done, will be doing this mistake that you will draw this curve here. That is, it is looking very good, right? But that will not be the case. Okay. So can you see one thing, that for both of these cases, one thing is constant, that in both of these cases the slope is decreasing. That is, the change in temperature with respect to x is decreasing. But because this is increment in temperature and this is decrement in temperature, this is convex upwards and this is convex downwards. Okay. Now one more thing, if you having any confusion, this graph you are drawing, okay, the thing is that this rod is continuously moving, that is true, but I am drawing this curve for a particular case, that is, I have taken a snapshot. Okay, I have taken a camera snapshot, then at that snapshot, at any x there will be a temperature difference. Here it will be T ambient, here it will be 25, here it will be 35, here it will be 40, 50, here it will be maybe 70, here it will be 80, here it will be 90, here it will be 50, here it will be 40. This is a snapshot I have taken. Okay, so that is why it is happening. হ্যাঁ কে আসছো, এসো এসো, কি হয়েছে, আয় আয়, কিছু বলবি? হ্যাঁ আমি করছি রেকর্ড, কিন্তু ইটস ওকে, দেরি হবে না, আমি এক্ষুনি চলে আসবো। ইটস ওকে, এখানে আরো সুন্দর আমি 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 করে নেবো, অসুবিধা নেই। Again, sorry for that. Okay, so I hope this is clear to you. Okay, now you have to find this t as a function of x. Okay, so now there are two approaches to this problem. I will solve this problem in the next lecture. Okay, because I have to go in my campus. I am having my train in 12:50, so I have to be ready. Okay, so I will just talk about the approaches. Okay, and actually I have to go now because it is already 10:16. I will be late. Okay, but still I will be just talking about the approaches. One approach is, I will be just talking about this. Okay, you don't have to worry, I will be solving the problem in detail. One approach is, you are sitting on the sheet. So just literally imagine yourself as a molecule on the sheet. So then what you will feel? So you are entering the furnace. So before entering the furnace, you are like, okay, it is very comfortable environment at 25 degrees Celsius. But at the moment you are entering the furnace, suddenly a shock of 100 degrees Celsius. Okay, suddenly a shock of 100 degrees Celsius. So it is like that if you are going into a military training camp. So from the first day they will make you to wake up at sharp 4 a.m. and you have to run for maybe 10 kilometers and all. So that is a very high amount of shock for you. But after some days you have already accustomed with that shock, and now you are okay. Now the difference between your body clock and your energy and the energy that they expect from you is not very more. The same thing is happening here. You are the molecule sitting on the sheet. Now that is your reference frame, that is you are the molecule, and with respect to you, what you will observe, with respect to that I will be solving the problem. Now you tell me that what you are saying, that now I am sitting on the rod, so I am entering in the furnace. So I am entering in the furnace at 12 o'clock, and at 12:15 I am at the middle of the furnace. So now my temperature is not same as ambient temperature, my temperature has increased, and at 12:30 I have just going out